Page 320, number 23. This question is going to need to use this identity 1 minus 2 sine squared x equals cos 2x. And we'll get to that a little bit later, but this is a double angle identity for cosine. So this question gives us the arc of y equals sine x and the line y, or the line y equals 0, or the x-axis. So that area yellow that I've shaded, we're going to rotate that around the x-axis and we're going to generate a solid. So when we rotate this, we're going to get a cross-sectional, our slices are going to be along the dx. So I'm just going to draw that in. So I'm going to have slices, vertical slices like this along and give us width of dx. And those slices are going to have cross-sectional areas of circles. So we're going to need to calculate the area of the circle and then give it some thickness. Okay, so when we set this up, the radius of that circle is going to be the height of that graph, which is r equals sine of x. So setting up this volume, the volume is going to be pi times r squared. So r is going to be sine x, and we're going to square that. We're going to give it a thickness of dx, and we're going to integrate it from 0, and the x-intercept is going to be at pi. 0 to pi like this. Okay, so there's the integral that's going to calculate the area. Now, the problem with this integral is that we're not going to be able to anti-differentiate sine squared x. There is no known antiderivative that we have for this. We can't use a substitution. There's no techniques that we can use to deal with this. So what we're going to do is we're going to go back to this expression here, and we're going to use this identity. And we're going to use this identity to convert this sine squared into cos 2x. And we can anti-differentiate cos 2x. So when I rearrange this, I'm going to end up with 1 minus cos 2x. Okay, that's going to be equal to sine squared x, 2 sine squared x. And so we're going to divide this by 2. And so we're going to come up with this, we're going to replace the sine squared x with a 1 minus cos 2x. So this is what it looks like. We end up with v equals pi 1/2 minus cos 2x over 2. Now I probably could have kept that 1/2 on the outside. In fact, let's do that. Let's make this a little bit simpler looking. So we're going to factor out the 1/2. So we end up with pi over 2. And it's going to be 1 minus cosine 2x. And that we've replaced that sine squared with this expression. So I'm just going to highlight this. So this expression here, sine squared, we've replaced it with this expression here. And we got that from rearranging that identity. Now we can anti-differentiate this now. So we end up with pi over 2. The antiderivative of this, make sure I put my bounds in. Antiderivative, I'm going to get x minus, the antiderivative of cos is going to be sine. So we get sine 2x, I just have to remember to divide by 2. And then I'm going to do this from 0 to pi. And I can now evaluate this integral. Pi over 2. I end up with pi minus sine of 2 pi is going to give us 0. Minus 0 minus sine of 2 pi. So minus sine of 0 is going to give us 0. Okay, so when I plug that all in, I'm going to end up with just, looks like it's just going to be pi. My volume works out to be pi squared over 2. That's going to be units cubed, ends up being my volume. So the answer works out to be B. And this answer requires us to be able to recognize, first of all, that we cannot anti-differentiate sine squared x. If you tried anti-differentiating that, that's when we're going to run into problems. But we can use an identity, this identity here, to rearrange the sine squared x to equal 1 minus 2 cos x. Well, although we can't handle the squared on the outside, we can definitely handle a horizontal compression of 2. And that's essentially what this double angle is. It's just a horizontal compression, which then allows us to anti-differentiate this expression.